Hello, my lovely students. So what we're going to look at is some Chapter 7 stuff. So these are some of the principles that are nice to know before fully digging into Chapter 7. My apologies for this coming out so late. So one of the first principles we have is the multiplication principle. So this principle is like we very often use this kind of innately when we're figuring out how many possible outcomes of some particular weird math experiment. So the fancy, suppose there are m possible outcomes for one process and n possible outcomes for a second process. The total number of possible outcomes for the two processes combined is m times n. And you can see the example down here with the coin flips. So there's two choices for the first coin flip and then two choices for the second coin flip, but those get multiplied. 2 times 2 becomes 4 choices. If we add in a third coin flip, now it gets doubled again, 2 choices, so now it's 8. But there's a lot of different ways this can show up. And I've got some examples from down in the text below. So a local ski shop sells, doing 14 here, 9 types of skis, 8 types of bindings, and 12 types of boots. How many different ski binding boot packages are available? All right, so we have skis, and the choices are 9. Then we have the bindings. There's 8 different ones of those. And then we have boots. And there are 12 types of boots. So if I was actually going to like name each of these skis, I'd have 9 different positions. And then I'd take my bindings, and from each of those 9, I'd branch off 8 times. And then from each of those, so I have 9 and each one has 8. So 9 groups of 8 is 9 times 8. And then that 9 times 8, which is 72, that many groups, and off of each one of those endpoints, I'd split 12 times for the 12 boots on each one. So this is where we get the other multiplication. So sometimes this is what we want on the bottom number for total possible outcomes on some of the probability problems you guys are going to be playing around with. And because there's only so much multiplication I can do in my head. So that is 864 ski binding boot packages. Now the food ones are some of my personal favorites. So a restaurant has a special menu, Chili's, that features 2 choices of salad, 8 choices of entree, and 6 choices of dessert. Well, actually, Chili's is a little bit different. So, salad, you only get 2, which is going to be House or Caesar. It always is. More choices on the entrees. There's a bunch of Italian places that do this too. I mean, well, Olive Garden, it's actually like 4 different soups or the salad. You can actually ask for no dressing, though. They give you a funny look, but the amount of salt in that dressing is insane. And then desserts, the most important part of the meal. So eat your salad, get your entree boxed up, sneak 1 bite of it, and then eat your dessert. That's how to keep your calories down. So 2 times 8 times 6. This one I can do. That's 48, and twice 48 is 96. So there's 96 different choices. Now this brings me to 2 of my favorite thoughts. One is Sonic finally put the important word on their shirt. It used to say like 1 million blah, 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 blah possible drink combinations. And I think finally a mathematician emailed them and got annoyed because that number is always like 2 orders of magnitude too small, meaning it should be like 100 million. So they put the word over 1 million possible drink combinations, and now the mathematicians can't complain anymore. Whataburger had the same thing for a while. There's 1 million blah, blah, blah ways to have your burger. And I calculated and I was like, no, you are so under. So, fun fact. This is what's going on. It's just the number of different choices again and again and again. Like it gets kind of crazy. Like 72 is how it often looks when you're doing this kind of thing. So the car model you are considering comes with or without leather seats, with or without a sunroof, with or without window tinting, with or without cheese, and in 8 stock colors. Okay, not the cheese, but that's what it's like with burgers. So you have all of these with or without, with or without. So you get one of the two. So we have leather seats, sunroof, window tinting, and then the 8 colors. So this is actually 2 times 2 times 2 is 8, times another 8 is 64 different versions of the car. Now the reality is when you go to the car lot, there's only like 4 that are right there. So this is one of those, if you were going to order your car from scratch, the way they used to do for Saturns, ooh. But they don't anymore, sadly. And then 70, you're required to take 5 courses, 1 each in humanities, sociology, science, math, and music. And this is actually fairly accurate. So 4 different humanities, 3 sociology, 5 sciences, only the 2 math courses, and 3 music courses. And so we would literally just multiply that insanity, and I ain't doing that myself. So let me just type in here. 4 times 3 times 5 times 2 times 3. So there's 360 possible schedules. And your freshman advisor will try to shoehorn you into one of those 360, regardless of what your degree is going to be. Literally, I had that happen. They tried telling me, you need to take college algebra. And I said, I got an AP credit for Cal 1. No, I don't. I had to go get the math department head signature at my school for them to stop saying the silly things they were. Yep. Now, sometimes instead of dealing with just the multiplication principle, we're going to deal with this new operation called the factorial. So let's flip this down here. So we're going to talk about in 7E permutations, but what comes up here is that permutations talk about when the order of an arrangement matters. Meaning if I was choosing 3 letters, ABC is different from CBA, different from BAC. There's actually 6 different ways you can rearrange those letters. And the reason I know that is because it's 3 factorial. Now, the way a factorial works is you start with whatever number you see, and then you multiply it by every number until you get to 1. So the factorials get huge real fast. The only other weird fact, so the way a factorial works is I think of it as how many ways can I arrange books on the shelf, or candles on the shelf, I think is one of the ones Alex does. So if I have 7 books, and I'm going to put them all on the shelf, how many ways can I arrange them? So if you think of it as, well, I'm going to put the first one up there first. So you pick the one for your first one. How many did you have to choose from? I had 7 books total. So I had 7 to pick from. All right, so plunk, there's our 7. Now you've put it on the shelf. So now you're only holding 6. So for the second book, you have a choice of 6. And then for the third book, you have a choice of 5, and then 4, and then 3, and then 2, and then 1. So mathematicians got tired of writing that as a big giant product, because then you've got 6 multiplication symbols even in there, 5 even if you drop the 1 off. And mathematicians are too lazy. So that's when it became 7 factorial. Now we're going to see that pop up in a number of different ways, but this is something you can crunch on the calculator, but you have to be careful. And I say that because it gets big so fast, sometimes the calculator won't be able to handle intermediate steps well. So we're going to have two particular operations, permutations and combinations, that are going to use factorials inside. And a lot of times it is actually better to kind of write it out by hand, do some cancellation, and then plug the leftover stuff into the calculator. But we're going to see something similar to that down here. So this is a review of factorials, assuming you've seen it somewhere. All right, so they give us a couple of fractions here, and they say do it without using the calculator, meaning these are not going to be as bad as they look. So 6 factorial over 4 factorial, they wrote it all out, and then notice everything in the 4 factorial canceled with some of the numbers from the 6 factorial. In fact, everything from 4 down. Everything from 4 down was 4 factorial. So we were just left with 6 times 5 on top, which is 30. 25 factorial over 22 factorial. Well, I can think of 25 factorial as 25 times 24 times 23 times 22 factorial. And now I don't have to write anymore and cross, cross. Then I just multiply those three large numbers. 200 factorial is insanely huge. Don't punch that. Your calculator is just going to like barf at you and be like, too big, error, overflow, something like that. Don't even put it in Excel. It'll just make your computer have the spinny wheel of death way too long. But 200 factorial divided by 199 factorial? Oh, that's almost all the numbers getting immediately divided out. So you're just left with 200. So the kind of lesson here is don't freak out if your calculator panics about it, because a lot of these you cancel a bunch and then you just need to crunch with the remaining numbers. The other nice thing is these work out to whole numbers, because we're saying how many ways can I arrange something on a shelf? That is going to be a whole number, a positive integer, not a fraction. There's not 2.5 ways to arrange something. Now, the interesting side fact is, if I have no books, how many ways can I put no books on the shelf? 1 way. I did nothing. It's an empty shelf, but that is counted as 1. So odd fact is that 0 factorial is indeed defined to equal 1. And it comes from that idea of there's 1 way to arrange nothing. So it's kind of a vacuous default 1, if you will. 1 factorial is also 1, because you put 1 object on the shelf and there it is. All right, so here we've just got some crunching practice with factorials. And in particular, I want to look at 17 and 19, because we are going to see problems like that, and then 15 and 16. So let's start with 15. So 12 factorial on top over 4 factorial times 3 factorial. So I know the 12 and the 4 factorial, I can at least write my 12 all the way down to 4 and then cancel from 4 on. So that's the first thing I do, is I pick whatever my biggest factorial on the bottom is, and I start writing the top until I get to that number. So it gets a little tedious. In fact, it gets a lot tedious. But there we have finally arrived at the number. All over. I'm going to move the 4 factorial over here. And then the 3 factorial I'll go ahead and write out. So those guys, turns out it's 24, but that's something they reduced by. Then the 3 times 2 here is actually 6. So that 6 gets canceled off and we're left with all the rest of those numbers. And this is why we give you a calculator. Please do not crunch this by hand. If I give you a problem where it's like this long, this is why you turn in your scratch work. If you don't have a calculator, you'd say, this is my answer. I don't have a calculator, so whatever this would come up to is the answer, and I will give you full credit for that. I don't want to penalize you guys because you forgot your calculator. Or if you make a numeric error doing the calculation by hand, as long as you turn in your work and I see that's what happened, you'll get full credit. I did that on that test recently. All right, so let's crunch this. 12 times 11 times 10 times 9 times 8 times 7 times, skip 6, 5. Oops, sorry, equals a lot. So over 3 million. Now, if we do the crazy 16 there, so a 9 factorial over 4 factorial and 2 factorial. And it's going to look very, very similar. So we start 9, 8, 7, 6, 5. There's the 4. So I move the 4 factorial on the bottom over there. And then 2 factorial is the very boring 2 times 1. So cancel, cancel. And then the 2 is just going to divide into one of those even numbers. So I'll go ahead with the 6. It's smaller. So this is now a 3 instead. And this is, of course, a 1 on the bottom. So all of these factorial questions, when we're talking about the permutations and combinations, these all work out. Everything on the bottom should cancel with something on top. So that's one of the reasons why I say write it down, simplify it, then crunch the results on your calculator, because trying to crunch this as it started can be a bit much for many calculators. And instead of 6, we have times 3 times 5. And you could also 9 times 8 times 7 times 6 times 5 divided by, in parentheses, 2 times 1. You could do that as well. So 7,560. All right. So let's take a look at 17 and 19 there. So the reason I am saying these is because we're going to see problems that have this format where we've got a large factorial on top and then 2 smaller ones on the bottom, but it's presented as the difference between the 2 numbers we had. So not going into the details of why we would do that. I will do that in the 7E video if you wanted to look. So the 11 minus 3, that's the way the formula reads, but you can just simplify that to 8. And note the factorial is outside the parentheses. So our order of operations, do what's inside the parentheses first, then the factorial is a multiplication order. So we have 11 factorial over 8 factorial, also with the 3 factorial. So that is going to be 11 times 10 times 9 times, and there's our cancellation. And then 3 times 2 times 1. So ugly factorial part gone. This totally legit to crunch on the calculator. 11 times 10 times 9 divided by 3 times 2 times 1 in parentheses, or divided by 6. But the 3 will cancel with the 9, leaves us with the 3, and the 2 goes into the 10 5 times. So we actually end up with 11 times 5 times 3. So 5 times 3 is 15, and 11 times 15 is 165. And then same song, second verse up here. We're going to have 5 factorial on the bottom, so 8 times 7 times 6 times the 5 factorial, but it cancels, so I get lazy, over 3 times 2 times 1. 3 times 2 cancels the 6 out. You're left with 8 times 7, which is 56, because 5, 6, 7, 8. I do too much mental math. So that should give you kind of a down and dirty idea behind the multiplication principle, which is how we count outcomes, like the rolling 2 dice. There's 6 choices for the first die, 6 choices for the second die. 6 times 6 is 36. 36 possible results. All right. See you on the next one.